In the next section, we'll look at some simple first parallel algorithms, and we'll look at the string matching problem, which you know from Unit 4. But this time we'll look at it from the parallelization angle. And it will turn out to be a relatively easy problem. And what I want to introduce here is a term that's it's maybe a bit funny, but people kind of stuck with it. We call problems embarrassingly parallel if they're very easy to parallelize. Slightly more detailed, what we mean by that is the overall problem can, without much effort, essentially immediately be split into many small subtasks, and each of them can be solved independently of each other. And the second part is important. They have to be solvable independently, because that means we can do them in parallel. If there are any dependencies that one task needs the result of another one, then parallelism is tricky. But in an embarrassingly parallel program or a problem, that doesn't happen. The tasks are all nice and independent. And a prototypical example is summing up two matrices. It's maybe not such an exciting operation. Everyone's doing matrix multiplies. That's what machine learning inference is. But if you just sum up two matrices, the sum of a matrix and another matrix is the entry-wise sum. So you can just compute each of the entries in the output separately by taking the respective entries of the input. So that's a prototypical embarrassingly parallel problem, and you can write a simple algorithm for that that just does this loop over the output cells in parallel. In a way, that's almost by definition the best possible case for parallel computation. We haven't talked about independence that much yet, but what else could you speed up other than doing many things all at the same time? And the easiest for that is if they don't have anything to do with each other, and they can just be done one after the other. Now, not all problems are like that. Sorting, in a way, is not really like that. At least we haven't seen any way to easily break it into small problems. There may be parts of sorting that are like this, and we'll come back to that. But if you take the problem as a whole, it's not clear what would be a subproblem of sorting that you can solve independently of the others. And the overall problem is still solved by solving all the small problems. So it's not always that easy. So we have two options now. What do you think is the true part for string matching? I mentioned it's a relatively easy problem, but maybe it's not as easy as matrix summation. Yeah, I think we have roughly the number from before. So let me share the results now, and we'll come back to that. I won't tell you yet. Let's have a look, right? Let's think about it a bit. So first of all, of course, we talked about this problem string matching before in detail. Sorry. I'm back on the slides. Welcome back to the slides too. We'll discuss the question in a second. We talked about string matching in detail. Now, we've seen simple things like the brute force algorithm, but that wasn't really the most effective way to solve the problem. And everything we've seen, in particular things like the Knuth-Morris-Pratt algorithm, they have a somewhat inherently sequential component. They became fast precisely by reusing the comparisons that we've just done. And they were exactly trying what the brute force algorithm did not do well, namely learn from the comparisons that they already done in the past. But in a way, that's exactly what you cannot do in a parallel algorithm. At least having these independent subproblems smells like the opposite. So what can we do? In another way to look at the problem, there is some independent subproblems, namely all the guesses in the terminology of Unit 4. We can try to find for all different positions in the text whether or not there's a match of the pattern. So here we'll look at this formulation where we find all occurrences. That makes it a bit more natural here. So we can take as one subproblem checking each of the guesses. So a simple algorithm that follows that approach would be like this. So the first one is a for loop, and it looks otherwise essentially like our brute force algorithm from Unit 4. But I've added here an in parallel. So that's the way how we program PRAM, the PRAM machines. We can use for loops and say in parallel, and what that means for the machine for running this pseudocode is assign each of the values of I a different processing element and do the loop body in parallel. Okay? It's a slick and short, concise way to do this. There's essentially also languages that do roughly that. You have to pay more attention to details though, but it looks otherwise very similar. So OpenMP is a library for C or C++ where you can use parallelism. It has many pitfalls, but that part is easy. And the rest of the algorithm is like in the brute force method. So for each of those guesses, we have to iterate through all of the positions. And we do all the checks. And if we found a match, then we report it. And at this point, you see, it would be inconvenient to try to now find out the earliest match. So instead, we just report all the matches. So happy? Is that a good algorithm? It's okay from the perspective of span, because instead of spending time linear in the length of the text, which is usually much bigger than the pattern, we just spend time proportional to the pattern, even if we do it simply as in here. And we can actually speed this up further. You'll do this in the tutorials. So instead of doing this simple loop, the way so this code has that span, because each of the iterations of the outer loop still has this inner loop. But you can speed up the inner loop further, at least if you allow certain concurrency on the accesses to memory. But the big problem is the work, because that's much more than what we can do in the sequential setting. So here we have the product of m times the work for each loop times the number of iterations. And that's essentially like the brute force method. Now you could say, forget about work. Span is great. I don't care about work. But remember Brent's theorem. You must care about work, because you're not usually running on millions of processing elements. You're running on a few dozen. So the overall time would really be this plus that divided by your number of processors. And so if the work is almost like the sequential, if the work divided by the number of processors is almost like the sequential running time, you haven't gained anything from parallelizing it. So that algorithm is not that great. At least it's not that great if m is not tiny, right? Now we can do better. We can, instead of doing each guess individually, we can break the text into blocks and use something smarter within the blocks. So that's the first kind of general trick. This kind of blocking technique will come up in other examples. And it's the first non-trivial technique as well to do better. So the important bit is that the blocks are overlapping. Each of those has 2 m characters, not just m. But we start every mth character. So we double cover the entire string. That looks like this. So we take the first 2m. And then we take these 2 and these 2. Right? It looks like a brick wall all the way through. Now we can discuss why we do that in a second. But then for each of the blocks, we again do things in parallel. But then in each block, we use a fancy method that we've learned about before. We call our KMP algorithm on just the little block of the text and the pattern. And we return whatever that returns. So why do I need these overlapping blocks? For that, maybe I want to make my picture a bit more accurate. I guess there's some boundary conditions at the end, but you have to just fill it up. So the lengths of the blocks are chosen to be 2 times m, twice as long as the pattern. So my pattern should be something like this, roughly that length, half of the black boxes. Now, if I only had this first row of boxes, I wouldn't find the occurrence of this pattern here, because it's not entirely within any of those blocks. But if I double cover everything, no matter where I try to hide my pattern, there is one block where it's contained entirely in the middle, or at least all m characters are covered in one of the blocks. And so one of the calls to KMP must find that occurrence. And so we can report it from there. It has the slight nuisance that if you're not careful with the blocks, you might report a match twice. But if you choose them like here, so that they never overlap in exactly m characters, then it works out. So let's analyze a bit how well this works. First of all, we have to do this loop, the overall loop, n over m times roughly. Within big O, the rounding goes away. And inside of here, how much time do we spend? This is constant time. And this one, now you need to remember what the running time of KMP was. It was, for text of length n and a pattern of length m, the running time of KMP is n plus m, order n plus m. So if our text has length n and the pattern has length m, then that's the running time of KMP. Now, what is n and m in our case? M is the same, but then the text is only how long again? It's one block, 2 times m, right? Yeah. So that's still linear in m. So each of the loop iterations has time m, and how many iterations do I have? N divided m. So the overall running time is linear in the total size of the text, or the overall work. Sorry. For the time, for the span of the problem, we do all of these in parallel. So the span is determined by just one of the loop iterations. So it's just this one. That's what's written there. So is that a good algorithm? I guess here it kind of depends. Well, first of all, for coming back to the question, let me show it again. guess maybe now you can tell. I mean, embarrassingly parallel means that we don't have to do the fancy KMP trick even. And so we're bound to the simple method from before, where we just do all the checks in parallel. And then that's only really a good algorithm if the text is much, much longer than the pattern. And for the KMP version here, span M is okay if M is small. If M and N are roughly of the same length, then we haven't gained anything. Then the parallel algorithm is not much faster. If N and M are roughly the same, nothing is 1. Okay? But if... Question? Okay. Okay. Yeah, so the typical example of string matching would assume that the pattern is much smaller than the text. But yeah. So what can we say so far about string matching in parallel? The methods I've shown you are fairly simple. Once you know KMP, the code was just a few lines. But these already work reasonably well. I mean, under the assumption that your pattern is not enormously long, but if the pattern is reasonably small compared to the text, they give you a lot of speed up for parallelism. Can you do better? And it turns out you can do better even if the pattern is long, but it becomes a really tricky theoretical question. So there's several barriers that you have to overcome. If you remember what KMP did, it does a pre-processing step on the pattern, and you have to speed that up as well, or parallelize that to be better than theta M span. And also the matching part, when you try to find your occurrences in a block, that has to be sped up and parallelized. And so it turns out this is a theoretical possibility on the PRAM, but the algorithms are, as far as I know, not practically relevant, and a bit beyond the scope of the module. But as in many occasions before, I don't want to leave you with the impression that what we've seen is all there is possible. You can do better, but it's much more complicated, and it's not clear if it gives you a speed up in practice. But that doesn't necessarily stop the question from having a positive answer in the model. So here's just for reference, the state of the art as far as I know. And then it depends on the model again. You can do, instead of M, log M time, so an exponential improvement, if you want to phrase it like that. And if you have this concurrent writes, then you can even speed up things further. But again, this is not part of the exam material. It's just for your curiosity and interest.